Now it's full screen.
Yep.
Good. So this is indeed a talk I gave last year at ISO for the ISO staff. So I have not prepared something especially for you because I thought it was fitting fairly well the subject. This talk was to summarize my career at ISO and everything which has been developed with my colleagues during all those years. And this covers finding a site for an observatory. I started with a VLT and then there has been the ELT. Developing tools for the operation of the observatory and thinking about the future. So I will just deliver today this summary of all those developments. So as I said, 30 years ago, ISO decided to embark on building what was called a very large telescope, or 8-meter telescope. It was a very big project, much bigger than anything ISO had done before. And for that, they understood that the choice of the site would be very important. And they opened a position of atmospheric scientist or physicist, which I took. And since then, I've been working at ISO for this topic. You see, the difference between ISO and other observatories is that normally for site testing, you have one astronomer in charge, do a few years of site testing, and then goes back to astronomy afterwards. That was the case in all American, for example, American site testing. For the first time, ISO decided that it was important to have somebody full-time. And I think it was a good idea because it has allowed us to continue developing between the site testing to develop tools which are now implemented in the control room and acknowledged by the users as very useful. So one FTE, that means one person full-time, has been allocated during all those years for site testing, monitoring, and various activities which are related. And of course, the aim is to make observation at ISO better. And I must say that as we have seen in the talk by Cassiana, that IEC is doing something very similar with a competent team on site monitoring. Okay, so this talk is divided in 3 parts. Of course, I will not use the whole hour, but I hope there will be many questions. So there will be time for questions afterwards. So the first question is, of course, related to this workshop here. Why are the observatories where they are? Or how can we decide where to put to build a very large facility? Then why should we continue monitoring the site once the telescope is built? So what does that help for observatory operation? And then this is fairly new. Cassiana has talked about it, the forecasting of observing conditions. Is that useful? Is this something we should invest in? So the first talk by Kemal, I think, has described a bit what could we do with this tool named FreeOwl. Why did we develop this? I would say for the ELT, there was no predefined area in the world where we should focus. It was clearly said, please look around everywhere and let us know which are the areas of interest for this extremely large telescope. So for that, we needed a tool, and it has been, as was said, developed collaboration with the University of Zurich and of Freiburg first, and then Zurich afterwards. And the name FreeOwl is historical. Free is for Freiburg, it was the name of the university where the PhD student was, And OWL was the first name of the ELT. It was named Overwhelmingly Large Telescope. So, and it was a bit larger than what is ELT now. Okay, so the idea was to use all the database available to compile all that within a tool, GIS, the Geographical Information System. I think for the astronomy, it was the first time that such a tool was used. And the advantage of this is that you can query all areas with a given altitude more than so much, with cloudiness less than so much, precipitable water vapor less than so much. And then you come out with a map showing you which areas propose all those criteria, fulfill all those criteria. But the question is, how do you set the criteria? And Cassiana just said it. I mean, you need to know what you want to do, which kind of astronomy. So science requirements is a starting up for site testing, whether it is infrared telescope, sub-millimeter, or millimeter telescope. It makes a big difference, and the results will of such tools like FreeR will not be the same, of course. Once you have all those criteria, and you can select the main areas. Of course, as was said, the resolution 2 by 2 degree is not very good, but the new release of the meteorological model is now a bit better. So the current FreeR is using ERA 45, so 45 years of data recompiled from the European Center for Medium Range Forecast meteorological model, but there is no available more accurate model with a higher resolution. So 45 years, I said, is it enough to check climate stability? Indeed, it's not really enough. It's can help a bit to see the variability, but I would say 45 years is too short to show the trends like global warming or so on. But at least you can see the cycles. For example, in South America, we have this El Niño cycle. It is clearly visible on the 45 years database of the ECMWF. The new, I think the new available data set is a bit longer. The idea is that those, the model, the current model, the most accurate and up-to-date model, is replayed on ancillary data. So 45 years of data have been used to initialize the current model of ECMWF. And it gives a very homogeneous data set over the years, which is what we need. So it was clear from those data that, and it was said in the first talk, that the area of Egypt has a potential, and that is why this meeting is very interesting. And that is why this project of the large telescope in Egypt is certainly very reasonable, I would say, because there are sites which can house such a large telescope. When you do a site testing, of course, you select the sites, and then you have to measure them. You cannot deploy instrumentation on many mountains, so it really has to be reduced to only a few. In the case of the ELT, we had a number of, at the beginning, something like 10 areas, including Antarctica. And we had a program, FP6, it's a European funded program, which allowed us to make a collaboration with the University of Nice, with AIC, Morocco, and this gave us the possibility to study with the same instrumentation about 4 sites or 5, several continents. So it was a very large effort, and which was only possible because we had a very good collaboration between all those institutes. Now, what do we want to develop? What kind of instrumentation do we need? We have already talked about this sky quality monitor. I won't talk about that. Precipitable water vapor monitor. Here I will just talk a bit about the thing because it was my first activity at ESO. To develop a seeing monitor, and I want to show I love this instrument. The very early differential image motion monitor developed in the 60s. It was a visual instrument. You look at the star through two opening, one here and one here, and the observer sees two images of the same star, and according to whether they overlap or whether they separate themselves, the observer could estimate the quality of the scene. This picture was taken at Majdanek Observatory in Uzbekistan, and in the rear, so this is a small Majdanek, which I call, which is a civil astronomical observatory, and here in the rear you see the big Majdanek, which is a military version. This, of course, between 60s and 80s or 90s, we could use the detectors, CCDs, and so on. So then we have made a version of seeing monitor, which is transportable, and a small telescope, and 2 subpupils on the primary mirror were used to obtain the same result, but the images of the 2 stars were projected on the CCD camera, and the differential motion of the 2 images in both directions, longitudinal and transverse, were measured at a rate of 1 or 200 images per second. So of course one can get results and values of seeing, but the question is whether it really represents what a large telescope would measure in reality. And that is why we had to convince the astronomical community that this new instrument could indeed characterize a site before the large facility is built on it. And for that, we had to attach a small 35 centimeter telescope to a 2.2 meter telescope at La Silla Observatory. And both have measured during a few nights. And we have shown that the correlation between the long exposure at the focus of a 2 meter telescope and the seeing measured by the differential image monitor was good enough so you could trust this instrument to do your site testing all over the world. So this was the start of the long life of the DIMS, the differential image motion monitors, which are now used everywhere in astronomy. The second thing, which is very important when we do a multiple site testing, is to make sure that the instruments which are deployed are identical and deliver identical results. By the way, it will never be absolutely identical because all we measure is the statistical values in the atmosphere. So statistics is not deterministics. That means there is noise, and even if you put like the TMT made in 2004, side by side, very close to identical systems, still you see a dispersion, but the correlation has to be one between the 2 instruments. And here we also have taken advantage to compare to another instrument which had been developed by CTIO in Chile. And we had a few also ESO instruments in this campaign, joint campaign between TMT, CTIO, and ESO. So I think it is something which is really recommendable to compare. If it's a new instrument, compare it to others which exist already. And also if you duplicate the instrument, compare it, because you never know. Many things can happen which could make problem in one of those. Then how long one has to monitor a site? No. Come to a bare mountain, you install, of course, seeing measurements cannot be made on the ground. The ground is too turbulent. The first meters are much too turbulent. So it would just add noise to your measurements. So it is recommended to have the seeing monitor on some elevation. There is no rule. We made sometimes 2 meters above ground. For example, measurement of seeing in Charnantor in 5,000 meter altitude in Chile. But if it's possible, a few meters, 5, 7, that is what people use normally. It has the advantage of having less dust, local dust. So you can have a system which is robotic, which doesn't need to be cleaned too often. And of course, it's better to measure during a long time. So TMT measured during 5 years. It is really a lot. I don't think it is necessary to do so long, but I would say a full year is good because you can follow up the effects of the seasons. And seasonal effects can be very large, in particular to places which have monsoon or other cyclical weather patterns. Measuring seeing is not enough. You need to have, in the same time, the basic meteorology, because very often the seeing is not the same depending on the wind direction. And when the telescope will be built, this is very important to know where you want to observe, which direction will you want to observe, and is this site good in the direction where you want to observe most of the time? For example, when it was the case in Chile for observing the Magellanic clouds and so on. Very large telescopes, of course, have no preferential direction of observation, but at least for the conception of the observatory, it is important to have the full history of the wind distribution and the related seeing distribution, if there is one. So we have done most of the time a few years of observation on all the sites for the VLT in Morocco, in La Palma, in Argentina, and in Chile. And only after this, we could gather the data and compare the site and build and choose it. Once the site is chosen, the observatory takes a few years to build it. So, but then many cases people have started to operate a large telescope and didn't think about continuously monitoring. At ESO, we have monitored continuously, and now it seems that people are very happy about it. If you, on this picture of the VLT observatory you see on the right, you have a suite of instruments here along the side, the northern side, where the wind comes from most of the time. You have here a seeing monitor, the original seeing monitor, which is not anymore used. Meteorological station, this mast, 30 meters high. It has to be at least as high as the highest of the buildings to measure a wind which is not perturbated. Then we have a slowdar, which is an instrument which measures the seeing, but also which is profiling the first tens of meters of the atmosphere, and this is important to estimate what is the seeing at the top of large dome. For the ELT, for example, the dome will be more than 60 meters high. We won't have a seeing monitor at 60 meters. It's a bit cumbersome to have such a high tower, but with a slowdown, you can measure the profile and remove the turbulence which is below the large telescope. So you can really estimate the real seeing seen by the large telescope from the aperture onward, upwards. So that is for the slowdown, so a low atmosphere turbulence profiler. Then there is a precipitable water vapor monitor. It's a radiometer. It's fairly expensive, but it's important because the GPS which are used in IAC are good down to 2 millimeter water vapor. But if you want to go to a fraction of a millimeter, then of course one need a more accurate instrument. And then if you continue on the same line, you have the new mass dim, which has been started a few years ago. This is a combination of the classical differential image monitor measuring the total seeing and the mass, which is measuring the scintillation of the same star through 4 concentric annular apertures. It was developed by Tokovinin and Kornilov in Moscow many years ago. And the combination of mass and dim, because mass is sensitive only to the higher layers and not to the ground layer, if you combine mass and dim, you can estimate what is the contribution of the first, let's say, 500 meters or so, which is important for the adaptive optics, because there is a type of adaptive optics where you want to correct only the lowest turbulence. And this mass dim gives you how much, what is the share of the total seeing, which is located in the what we call the surface layer or ground layer above the telescope. So this is, in my view, how large facility should look like. And in addition, this past 2 years, we are using one of the very VLTI, so the VLT interferometer telescope, 1.8 meter diameter movable telescopes, and we have attached to it a SIDA, which is a profiler of the whole turbulence in the whole atmosphere. So every time one of the auxiliary telescope is not used by the VLT interferometer, this telescope is parked over the pit where the SIDA instrument is there, and SIDA then starts operating. We have collected more than 100 nights thanks to this feature. So this is very important to have the statistics of the vertical distribution of the turbulence above the observatory. Don't forget that the ELT will be built at Amazonas, which is only 20 kilometers away from the VLT. So the high atmosphere is very similar between the two sites. So these statistics are then used by the consortia currently developing the future instrument for the ELT, and in particular the adaptive optics instrument. So that's it. It's a very complete suite of instruments, and it is used regularly in the control room. Here is an example of what the SIDA is providing. It's not only providing the turbulence as a function of altitude and of time. This is a complete night of observation. And in green, you have the wind, velocity, and direction in the same time as the turbulence. And this is, of course, very useful to be able to compute the coherence time of the turbulence. That means how fast does the turbulence flies over the observatory, which tells you how difficult it will be to correct it in a closed loop of adaptive optics. So again, why monitoring during science operation? You never know if your instrument or telescope is performing as planned. If you have an external monitor, it tells you how good you are. Are you able to retrieve the full or to use the full capability which is provided by the site? So here is an example of a very early example in the 90s during the first light of 4-meter telescope NTT at La Silla, where we were already site testing for the VLT, and we had a seeing monitor not far away from La Silla, a few kilometers away. And the team in charge of the seeing monitoring informed the team during the acceptance of the entity that we were just having a fairly good seeing conditions, so below 0.5 arcsecond, and so the first light team immediately took a picture, which you see here, and this made the first page of the Messenger a few months later, because this demonstrated that the telescope was able to deliver images as good as the site was providing. And of course, this is good information for a young telescope. Also, adaptive optics recently has been developed a lot and is very much used, at least at the VLT and in other observatories. And indeed, the adaptive optics is not capable to correct everything in the atmosphere. There are limitations. And of course, here I show that the stray ratio, which is the final result of the image quality after correction by adaptive optics, is better when the seeing originally is better. So the adaptive optics instrument will have better performance if you are on a site which has already a good seeing. And you see that for seeing above 1 arcsecond for this instrument, which is used and at this wavelength, the adaptive optics is not really improving much, while for very good seeing, the stray ratio becomes fairly good. Another parameter, in addition to the seeing, it was said already, the coherence time of the turbulence, how fast the turbulence travels above the line of sight. And this is also statistics of the stray ratio, but this time I think in the infrared. Showing that when the turbulence is very fast, so 1, 2, 3 milliseconds coherence time, the stray ratio decreases a lot, while for slow turbulent, slow atmosphere, you see that after about 4 milliseconds, practically the stray ratio is constant. So very fast atmosphere is detrimental for adaptive optics performance, and we know that this is very seasonal. We have more jet stream on the VLT above the observatory during the winter months than during the summer months. So you know already that instruments will not perform identically along the year. And also from one night to the other, there are huge differences, which introduces the interest of having forecast, because then, of course, you can choose the instrument most adapted to the conditions, observing conditions. Another important thing which was said already for monitoring precipitable water vapor is during science operation is very useful. Again, seasonal variation can be very well depicted, and for example, it's obvious that if there is maintenance to do on the telescope, you will do. Here in this case, it is a sub-millimeter telescope. You will do when the conditions are not very good, and keep the observations for when the conditions are very good. This is Apex in 5,000 meters on the Chernantor Plateau in Chile. what is in the, of course, it's not enough to collect data. You have to make it available to the users. So we have developed some graphical tools at ISO, which allow to depict the conditions. So coherence time seeing, everything which is measured in real time at the observatory. And we have added to that, you see it in green, the forecasts for which are delivered to us by the European Center for Medium Range Forecast in Reading in the UK. We get 4 times a day from the European Center data cube over the 3 observatories in Chile, and we extract the vertical profiles of all those parameters, not seeing, not coherence time, not yet, but at least all the meteorological parameters and addition precipitable water vapor. And this is displayed for the user so that the astronomer can take decisions during observation according to what is foreseen for the night to come, but also during daytime, the observations of the night are prepared, knowing what is forecasted for the night to come. And of course, the cloudiness forecast is very useful, very important, and I must say that recently CMWF has really made a lot of progress, and they are now able to give us even the band of cirrus passing only for 1 hour during the course of the night is well forecasted. Not always at the right time, sometimes half an hour more earlier or later, but at least it is very useful to know that the night might not be photometric all the time, so better use your time efficiently. Same thing for precipitable water vapor. The forecasts are a bit more difficult to for the precipitable water vapor, but still very useful. This is a bit old, I think in 2010. Now there are maybe better forecast. Here we have compared the forecast by 2 models, this GFS, American model, and CMWF. And you see that the 2 models are not completely in agreement. And in green, we have some measurements, local measurements. This is at apex at 5,000 meters. I think it's all I wanted to say on this. Now we come to the forecast. Of course, ideally, we would like to have to be able to forecast not only the meteorology, but also the turbulence, the seeing, the profile of the turbulence, where it is, how strong it is, and how fast it goes. Here is results of a feasibility study, which has been funded by ISO and made by Elena Machedri at Archetri, using a mesoscale model initialized by these ECMWF forecasts. But the mesoscale model is able to work on a very fine mesh, vertically and horizontally. Here you see Paranal and Amazonas, and the turbulence modeled above those 2 observatories. I think I have a zoom for that. Here is in the first 1,000 meters. So you see the accuracy of the model. It can really be very good. And of course, such models can be very useful for finding a site, for choosing a site, because they can go backwards in the past, use this ECMWF database to initialize the model at any time in the past and make statistics on the seeing expected on various summits and compare them before going to deploying instrumentation on the site. So the problem is, are they very accurate? And that was the purpose of this feasibility study, which was fairly long, 3 years of work, machinery, and there are many papers. Here is a 2019 paper, but just look at Machadri's paper and you will have a lot of information. Where those models are were not yet very good is for the high atmosphere turbulence. As you see, it's very flat, while close to the ground, it reacts fairly well. And probably it is due to the lack of vertical resolution. There has been much progress done, and there are other teams working in this field, in particular in Hawaii, in the Department of Meteorology. So I expect there will be a progress in the medium term, in the future, and to help this, to foster this progress, ESO has made a call for tender for developing such a model. Why is it so important to have this forecast of the atmospheric turbulence? Indeed, big observatories were expensive, and what we call the OB, the observing block, it's requested by the astronomers. They are filed for the night in a given order. And sometimes, of course, the OB is attached to some requirements from the scientist. So much, not more than so much seeing, not clear weather, clear sky, and so on, limited in water vapor, and so on. So all these constraints might not be fulfilled at the time where the OB is executed. This means it is lost. It will have to be repeated at another time. And this lost time is really very expensive time, which is long. So just reducing the amount of unsuccessful executions of OB would save a lot of money at the observatory, or let's say another way, would allow the observatory to give time to many other scientists. So this is a good motivation. And also the second thing is to optimize the short-term scheduling. And currently there is no real tool for automatically scheduling. It is the astronomer or the telescope observer who take decisions. And of course it can be fairly difficult. And also, of course, it depends on the efficiency of this decision-making depend on the observer. Its quality, whether he's fit, whether he's tired, and so on. So if we had a better forecast, it would be, of course, a way to relieve the night astronomer and to get maybe a more steady, stable throughput, science throughput of the observatory. So for all these reasons, this forecast tool, this call for tender is now open. The idea is to deliver a forecast for the next 3 nights with more accuracy, of course, for the coming nights. So the competitors, which are all external to ESO, will be given a number of nights for which they will try to forecast, and then we will compare to the conditions measured at the observatory. This is coming in the next months, and very interested by the results. So this is my last slide. I would say that as you have seen, the atmosphere is not a single piece. It's a lot of layers, and there are many influences on the final science quality of the observations. It's very important also the design of the telescope, of the dome. It is very important that there is what has been measured during the site survey is used by the designers to take into account the external conditions. It is very important that the dome doesn't add its own turbulence to the one of the sites. Yeah, it's a very challenging task which you are starting, and I think it's worth it. Thank you.
Thank you, Dr. Mark. Any question?
Yes, Nassim.
Okay.
Can you ask question, please?
Yes.
Thank you to Mark for your lecture, and I want to ask about the possibility of using the artificial intelligence techniques to forecast for the meteorological parameters that you talked about now. And as you know, the artificial intelligence is depending on the historical databases, and maybe we don't have this database in Egypt for monitoring stations. So how can we get this database from to use AI techniques in forecasting the different parameters for meteorological parameters?
Well, there have been some attempts. I don't know if it has been published, but at least in ISO Chile, they have a collaboration with Microsoft, as far as I know, and they applied AI on short-term seeing forecast, I think. And there were some results, but I'm not sure. Maybe Jason knows if it had been published or not. Apart from that, I don't know of any other currently applicable models, but the problem is that for short term, maybe it is useful. For the long term, the physics is really complex. What you measure at seeing is the sum of a number of events, which I think maybe artificial intelligence could be used on individual layers, maybe. But total seeing is something which is such a combination of many independent events, which I'm afraid will be difficult. But I don't know.
Jason, you have a comment?
Just to reinforce what Mark said, that indeed there is use of machine learning to do short-term prediction. So where you tune your algorithms to follow the conditions, but that's really following the airflow across your aperture. So this is really at the millisecond or second time scale. I think for medium level weather forecasting, which is what goes into site selection, I think there the historical record is not something that you regenerate through machine learning. I think that, and I'm an astronomer, that's a question really for meteorologists, not for astronomers. So that's all I could really add to that.
But maybe I can add for in the case where you still don't have any measurements, the meteorological models have a wealth of data. It is not complicated to dig into these big catalogs. For example, the CMWF has a catalog named Mars catalog, where you can find the profiles of all the variables over each of your candidate sites. And I really recommend to do this work because it's there. It's just help yourself.
Yes, Cassiano?
Okay.
Yes, no, yes, but I think that your question is very appropriate, but I mentioned some cases. Mark is also mentioning some possibilities. I really think that these databases, which are reanalyzes data, which include data, results of modeling, all that, I think they are very useful, and I think there are such a database is available with the resolution enough for the search. As I said, I mean, the one I mentioned, where I think it worked relatively well. And as I said, you have to somehow test the database so as to be able to confirm that it is useful for your particular place. I mean, you should somehow compare the data available with some local measurements. For instance, these balloon soundings or whatever, that for sure at your country there will be some. So once you are sure that it is behaving well, which I think, I mean, we did it and it worked well, I think these databases is for a search of different places, making maps at different heights that you can do, because as I said, there are several levels. And then you can have these databases at, say, 1,500 meters, 2,000 meters, 2,500 meters. And like this, you can somehow do the first search to compare the site you have in mind. I think this is feasible.
Another question, please, for Mark. If we already selected the sites that we are going to put our instruments, what is the starting point of the instruments that we should use as starting? You mentioned many instruments now, and some are old versions, and there are new versions of these instruments that we can use. What do you what is the instruments that you are going to encourage us to use as a starting?
Well, I will answer your question by a question. What do you want to do with your telescope? And then I can tell you. So first, what kind of science? What kind of telescope? What wavelengths and all this? And then we can define the instrument suite.
Suppose we will going to build an optical telescope with, as Cassiana said, with infrared measurements, and also with adaptive optics. So,
okay. So if you have adaptive optics, it's sure that what I've presented is what you need. So seeing and profiling the atmosphere is, want to know which is the part of the thing which you can easily correct with a wide field adaptive optics and so on. So mass dim is, or something equivalent is of course useful and necessary. Dim already alone is the minimum you can do. This you need.
Great, thank you.
Okay. Yeah, okay. Yeah. Yes.
I would just like to reinforce a little bit of this, because I've been listening to this conversation. You have decided, for good reasons, geographically, more or less, where your telescope is going to be. Yeah, so you don't have the option of picking the best site. You have the option of picking the best site where you are. And this is a perfectly reasonable problem to have. But I think there you actually have to do your comparative measurements with something clear, that you may find one site that is much better for something and another site that is much better for something else. And in that context, having decided up front what your criteria are going to be is going to be critical for you to navigate this discussion. It's unlikely that there'll be one site that will be so much better at everything than all the other sites. And this is actually a very difficult challenge. And if you have your science cases clear up front, then navigating that becomes something that is somehow easier. It's never easy, but it becomes somehow easier. I think that is something that is very worthwhile doing before you choose a site. One of the things, because Cassiana and Mark and everybody's talked about precipitable water vapor, the most critical thing for the infrared is the temperature. You can have zero precipitable water vapor at a hot site, you're not going to do good infrared astronomy. Okay? So these things you need to work out up front. And I think it would be super useful for you to have done that. You just say, these are the criteria, and then you can put some weights on them, and at least it will guide you. It won't solve the problem, but at least it will guide you. I think that was, an input into the process rather than the actual science.
Thank you, Jason. Indeed, we will come back to this discussion at the end of seminar, and we can go wide in the discussion, and in this decision must be taken by our colleague in Egypt. Mark, I have a technical question about scene monitor. As you know, this last year, there are some other scene monitor like polar scene monitor. What do you think about this instrument? It's very simple, and they can be used in several places at the same moment to make a good comparison. What do you think about polar scene monitor? Like,
you mean those scene monitor which don't need a tracking mount?
Yes, like
Okay.
like Cyclope developed by Cyril Cavador, as example.
Yeah. Okay. Well, everybody knows that it is not easy to make measurements on a bare summit and in the wind. Everybody has experienced this, and of course, at ESO we have been obliged to invest money to have very steady mounts for those FP6 for the ALT site testing, and this is pretty expensive if you need many of them. If you use only a tripod, which is sold with the Celestron orbit and so on, it's in the high wind, it will not allow you to work. So you will have statistics of the thing, but only when the wind is below 10 meters per second and so on. So yes, if the advantage of polar, it's on the northern hemisphere, while not using it, you don't need a mount. Well, I would say it's better than to have a shaky telescope. But again, compare it to a normal one before you start deploying it.
Okay, Dr. Ged, do you have any comments? No?
No.
No?
The next book?
No, I have a question.
Okay. You do.
Okay, thank you so much, Mark, for this very interesting survey about the instrumentation and this history. So my question is about the firewall software. Is it free for the new release? And the second question is, what about the current resolution for the new release? Thank you.
You mean the new release of ECMWF or what?
Yes, the new release of firewall software.
FreeRoll.
Yeah.
It is completely, the use is completely free, but it's nobody is improving it because we have no manpower for that. You are welcome to help improving, because FreeRoll is made in such a way that you just can include new database in the system if it is prepared along the line of the description of which is in the reference on the web page. You send me the database and then I can include it. So if somebody wants to help to install the latest reanalysis of ECMWF, I'm very happy, but there is no plan at ESO to do it.
Hello? Hello?
Okay, Dr. Said.
I have a question about using local meteorological station in forecasting astronomical conditions. Do you use data estimation system in making this forecast, or only using ECWF reanalysis condition?
Yeah. Okay, so ECWF is very good for what is the high atmosphere, of course, because there the mesh, the size of the mesh is not so important because everything in the high atmosphere is at a large scale, while close to the ground we have many small scale effects, and of course there, very close to the ground, the model is not able, of course, to reproduce exactly what you measure because the mesh of the model is what it is. Most of the time, your summit is not in the model. It doesn't have at all the same altitude. It's much lower because of this horizontal resolution. So what we do is that for local measurements, we apply a filter, for example, a Kalman filter, where we train the filter on the past few days or weeks, comparing the measurements to the forecast. So the filter is learning how wrong the forecast is, and is able to, or was, and is able to correct the forecast of the future, having learned this information. Yeah.
Okay. Thank you, Dr. Dave. Any more? Any question? Thank you, Dr. Mark. Next lecture. Next talk.
Will you take some rest, please? 15 minutes or so? No?
So
No.
I have another question.
Okay.
I'm sorry.
Okay, Dr. Said.
Thank you, Mark. I'd like to ask about again about the resolution. You said that in the current presentation, the previous one, we talk about the resolution of order, spatial resolution of order 1 or 2 kilometers. What about time resolution for astronomical turbulence? How time resolution we need to get a good view about atmospheric turbulence? We need in order of hours or minutes. Also, another question about how the large the domain, not the how much the area around the telescope we need to get to have a good picture about from our telescope about the spatial domain. Thank you.
So we talk about the mesoscale model. So the large global model like ECMWF is a model which covers the whole globe, and that has a resolution which is improving every 5 years. And so now I think it's 1/8 of a degree. So let's say 1-2 kilometers, or maybe 4 kilometers, I think. This is used to initialize a mesoscale model. And the mesoscale model is a model which covers a few kilometers around your observatory. Normally they are nested models. So you have a larger area with a lower resolution, and then the smaller and smaller areas, and the higher and higher resolution. The highest is something like 500-meter resolution in 5 by 5 kilometers around your observatory. And these models, so they are initialized by the global model, and then they run, the equations run every second, so they can really give you the time series of each of the parameters with a very fine temporal resolution.
Dr. Hadia, can we take 10 minutes for a cup of coffee?
Good.
Okay, as usual.
Okay, please
10 minutes.
stay connected and we'll come back in 10 minutes. Okay?
10 minutes.
Thank you.